All right, we're live. Thanks everybody for coming. So for a little bit of context, Ancestralize has been working disease by disease, and one of our first major topics has been insulin resistance and trying to incorporate that into our network and develop questions for the users. And really, there's a lot of different aspects to it, but the most important is really what our theory is, what we've discovered about insulin resistance, how that really plays within an ancestral mindset and functional medicine background, and really what the most important details are about insulin resistance so that we can translate that most effectively into our work. So this is basically just a quick overview, and I do mean quick. We're not going to spend a whole lot of time on each individual topic, but this is the major points of insulin resistance that we found. So without any further ado, he says as he can't change slides. Okay.
All right, so how do we define insulin resistance? This is the definition that we kind of came up with after searching the literature. And for us, Ancestralize, insulin resistance is the reduced sensitivity of cells in the body to insulin. As the cells stop responding, they become more and more resistant. And if this becomes quite widespread to different tissues in the body, then we can consider that the whole body or the body is insulin resistant. This is often accompanied by hyperinsulinemia, and if prolonged, it can result in impaired glucose tolerance and eventually hyperglycemia, which is too much glucose in the blood. So in terms of the frequency of insulin resistance, or IR, as we might refer to it in the presentation, if we're looking at it in the US, it's hard to measure directly what IR is in terms of prevalence, but we can look at the metabolic diseases or the diseases that are related to insulin resistance. So if we look at the population, about 38% have prediabetes and about 9.5 have type 2 diabetes, both of which are directly related to insulin resistance. And already that kind of tells us that it's about 41%. But then if we're looking at people who are metabolically unwell in general, that's up to 93% or 94%. So it's hard to, again, find direct figures, but when we're approximating it and what the prevalences might be, it's around the 94% mark in the population. Not accurate because we're not too sure, but we definitely know that it's quite high in the population, even if it goes undiagnosed. And so that's what we are assuming it is.
All right, into labs. So the first one, the hyperinsulinemic euglycemic clamp, is the gold standard to recognize insulin resistance. It is quite invasive. It's a medical procedure with a constant diffusion of insulin and glucose, so it's not very common in practice and not easy to prescribe, but it's the gold standard from which we detect insulin resistance and the response of the body to the glucose. The second one is fasting insulin. It's quite easy. It's a blood test and it detects the amount of fasting insulin after 8-hour fast. We set there a threshold for fasting insulin over 12, which is agreed upon in the literature, but the ideal fasting insulin would be much lower, maybe around 5, depending on the body mass and anthropometric variables. But yeah, that's maybe the first take to detect insulin resistant. Next is fasting glucose. Again, a fasting blood lab that detects how much glucose is there in a fasting state. It's very common to use in diabetes and pre-diabetes, as it's there that we mostly detect trouble with hyperglycemia or high glucose. That range of higher than 108 milligram per deciliter is higher than normal, and where obviously we can expect insulin resistance to be present. Home IR is index that uses both fasting glucose and fasting insulin. So it is not so precise because it only looks at the fasting state, although it's a good index and it's used in practice and in research. and it's maybe our next best after the gold standard. But again, it has its fallacies. The Matsuda index on the other side, so the home IR looks at resistance and the resistance of the tissues to insulin, but Matsuda index looks at the sensitivity, how much glucose can we clear off, and it includes fasting insulin, fasting glucose, and also a postprandial measurement of the situation. So it's much better, but more complex. The trade between the two is that the second has better like sensitivity, and it measures sensitivity, but it's a bit more complex to use. Then there is the OGTT, the glucose tolerance test, which is an infusion of 2-hour infusion of glucose that looks at how well the body responds to that infusion with using insulin to receive the glucose and store the glucose and move the glucose out of the blood. Again, a bit invasive, not the first choice. Triglyceride is not directly related to insulin and doesn't measure insulin resistance directly, but correlates really well and strongly with insulin. Better used as an index with fasting insulin or HDL or something else, but it's a strong correlation, so it's there. Yeah, that's it.
Sorry, Kaled, I probably cut you off there.
Cheesy, I think you've got a question.
Sorry, just a small correction. I think I understood at the oral glucose tolerance test that it was injection, but it's actually oral test. So you drink the
Yeah.
Yeah. Sorry.
My bad. Yes.
I know you know. I know you know. I just.
It's invasive in that people generally don't enjoy that test, but yeah, not invasive in that it involves surgery. Okay, symptoms.
Okay, so when we're talking about symptoms of IR, you can have early stage and late stage symptoms. There isn't as much research into the symptoms in the way that other diseases are researched, unfortunately. But when you have some of these symptoms, and especially if you have a combination of them, it can really point to underlying metabolic disease and underlying IR or insulin resistance. One of the first is this feeling of cravings, particularly for carbohydrates and sweet sugary food, and a constant sort of craving state can point towards it. Any sort of central nervous system dysfunction, so feelings of brain fog, difficulty concentrating, depression and anxiety can also point towards it. Weight gain as well can be an indication. Things like high blood pressure. So if you're getting high blood pressure even at a younger age, that can point towards it. And feelings of being quite tired, fatigued, getting muscle cramps, again, maybe an indication of insulin resistance and a kind of a flag for you to go and get checked out and see, is it going on? And of course, acne as well. And you can get acne in both men and women, but also with other things that are related, like polycystic ovary disease that could be closely related, where you can get the acne. In terms of late stage, you get dark patches, quite velvety dark patches in certain folds of the body, like around the neck, under the armpits. They're often known as acanthosis nigricans, and that could be a really important sign that there is insulin resistance going on in the body and for someone to be checked out with. And skin tags as well, although we often miss it and may dismiss skin tags as being related to something else. If you are getting it, and especially if you're getting multiple skin tags, then that can also be pointing towards early stage or late stage symptoms of insulin resistance.
Awesome. And to clarify, not everyone who has insulin resistance is going to have all these symptoms, right?
Yeah, you may have a combination of them, you might not have any of them. And also a lot of these are very non-specific, so they may point towards other diseases. So it could be like multiple months and years of searching for answers that might take you down different paths. But yeah, you can have some, you can have most, you can have none, depending.
Yeah, somebody watching this video with brain fog. It could be other things, but it could be insulin resistance.
Yeah, and we need to think about that as well.
Mhm.
So there are diseases where insulin resistance can be a causal factor. And again, because it affects, as we said, like you get body insulin resistance, it can affect multiple different organs all over the body. The key ones are, for example, your cardiovascular, so that's your heart and your blood kind of system. So things like hypertension or high blood pressure, clots in the blood, stroke, any issues with the heart because of the vessels that are kind of leading there and supplying that heart. All of these can be affected if you've got insulin resistance. It can also affect your neurological system, so things like dementia and Alzheimer's, they seem to be playing a key role, and there is a lot of evidence and research in those areas about that kind of relationship between insulin resistance. It affects your immune system, it affects your gut quite often, so you can get things like gastroesophageal reflux, so a lot of reflux and heartburn issues, even things like, for example, gallstones, maybe because of insulin resistance. And then we have all our metabolic diseases. So we know that it plays a role in type 2 diabetes, fatty liver disease, high triglycerides in the blood as well. Other key things to also think about, again, PCOS, that relationship is researched quite extensively. And then things like cancers as well. There are question marks as to whether insulin resistance plays a role and how that can help with prevention moving forward. And then finally, things like fibromyalgia, which is again a very non-specific disease that affects multiple systems, and whether that causal relationship and overlap of symptoms is related. So yeah, it's a lot. There's a lot there, but it's important to kind of note that it could be related, especially because it is a preventative thing that we can work on. So yeah, that's it.
Yeah, and this is largely a consequence because insulin receptors are found on every cell in the body. So
Yeah,
resistance to that signal can happen anywhere and manifest differently.
So yeah, that's the same, just kind of a lovely diagram to to break up the text, but it says the same thing that I've just mentioned. It can affect every part of the body, really.
Cool.
Yeah, not so lovely diagram here. So please, dear viewers, bear with me. I'll try to make a story out of this. So what is the mechanism and where does it first begin? Those three pictures on the right, the yellow bubble is basically representing our adipose tissue, where fat is stored mostly, because that's how we store energy mostly. Down left or down basically is a representation of our muscle tissue, which is where we might want to store some carbs, glycogen mostly, but also some fats. And then up there is our factory, the process place, the processing place. It's the liver that has to take carbs and fats, transform them, move them around, or at least move them out to the blood so that they can be either stored or used. Where does the problem start? Well, we're going to go into something that is called the fat threshold theory that has to do mostly with the adipose tissue. But I'd say it starts with overnutrition. So it starts in our mouth, actually. Overnutrition in the middle there, and especially carbs overnutrition, glucose with the arrow near it. So what does it do? It doesn't go all as carbs to the muscle, but actually it has to be, the excess of it has to be transformed into fatty acid. That happens in the liver, which is already a bit overloading the liver. The liver wants to transform and process energy and send it to storage or use, but hey, if I'm getting too many carbs, I have to do some extra work to make it into fatty acids that can be stored. Now that extra word means oxidation, means a bit of damage. And again, we get from it too many fatty acids. Those fatty acids are moved to storage in the adipose tissue. Now, the adipose tissue can take and take and take and collect those fatty acids, but at a certain point, it's overloaded, depending on our genetics and physiology and how our body is made. But let's say at a certain point, the adipose tissue gets overloaded. So we have what we call our own personal fat threshold being capitulated, ended. So the extra fatty acid that now we can store and the liver is making and packaging and moving out will end up in the muscles in the liver itself, in the pancreas, kidney, and in other places. The extra fatty acid will clog and make too many substrate inside the cells of each tissues that those cells won't be able to deal with and slowly build up insulin resistance. What does it mean? Insulin resistance basically means even if insulin comes and say, hey, I need to put in some storage material, the tissues will say no thanks. First in the adipose tissue, as we said, it's the first that gets overloaded and blocks the signal of insulin, say no more thanks. Then the muscle comes and say no more thanks. I can't take more fatty acids. I can't oxidate stuff properly here. I don't have space. And again to the liver. It starts to become a cycle, including mainly those organs and all the others, with again the liver producing too many fatty acids, adipose tissue saying no, and other tissues getting the burden. Yeah, so that's the vicious cycle. It starts with overeating, really starts when the adipose tissue is overloaded, and end up damaging everywhere.
Whew.
End of story.
Yeah. End of an incredibly simple story. Thanks, Kaled. So, believe it or not, Kaled just gave you a pretty big picture explanation, which it doesn't necessarily feel like it. If we were going to zoom in a little bit further, then we're really talking about mitochondria dynamics and overall mitochondrial health. So, this slide was actually constructed beautifully in that the A, B, C points actually correspond to the parts in the diagram. So to all you viewers, you're welcome. But essentially, to Kaled's point, we're looking at a substrate problem. Essentially that we have two competing substrates, glucose and free fatty acids, that are vying to be metabolized. They obviously have different pathways. So in column A, mitochondrial dysfunction, which includes reduction in mitochondrial content and mitochondrial biogenesis. First and foremost, mitochondrial health, which could be implicated with a number of things, including diet and lifestyle factors, also environmental toxins. If we have a overall reduction in the amount of mitochondria that we already have an issue with dealing with excess substrate metabolism, just because there are fewer places where it can be conducted. Accruing mitochondrial damage can just mean that even if you do have an acceptable number of mitochondria, they're functioning less well, and we can start to accumulate these damaging byproducts all that faster. Moving into B, we start to see that there is a strong component. If you're familiar with mitochondrial dynamics, you know that we're talking about the electron transport chain and the systematic movement of electrons to leverage more free energy from different molecule substrates. So a diminished electron flow through the ETC, electron transport chain, can subsequently cause electron leakage and superoxide generation, followed by oxidative stress. So the more that we rely on the electron transport chain as a natural consequence, we're not even in a dysfunctional area yet, free radicals and oxidative stress naturally occurs. And at normal physiological levels, they act as signaling molecules. So that is a normal consequence of the electron transport chain in cellular respiration, in that it actually informs your cells how much is happening and it can regulate accordingly. Where it becomes a problem, and again, this is a factor of excess substrate, this gets out of hand, and the amount of free radicals and reactive species starts to accumulate, which can cause cellular damage to the membrane, and overall cellular dysfunction. And this is happening. There are estimated hundreds to potentially thousands of mitochondria per cell in the body, and found in virtually every cell in the body. So this aggregate of damage can start to accumulate. What this actually translates to in C, this can lead to lipid accumulation. Largely that it's an energy substrate problem. You have too much of it. It isn't being adequately metabolized, so it starts to accumulate. This is where we start to see problems with ectopic lipid accumulation in different tissues. And it's essentially that there's an overabundance of substrate and no real mechanism to deal with it. So just a bit more of a granular view of what Kaled just talked about prior.
Okay, yeah, me. So why do some IR symptoms start before fasting insulin is high? Well, Kaled nicely went over this entire mechanism, and then Tyler went into mitochondrial dysfunction. So because the mechanism is a bit unclear, we tend to think that it can be due to these ceramides or other lipids causing low-grade inflammation. The increase of triglycerides due to impaired fatty acid oxidation can also cause issues, participating in early symptom development. And other small changes in the insulin state, resistance in general, can affect endothelial tissue, causing early changes in blood pressure. Okay, so as for inflammation, we're mostly interested in the white adipose tissue. If adipose tissue grows in a dysregulated way, the downstream effect can be system-wide inflammation. White adipose tissue contains not only immune cells, but also releases a lot of free fatty acids that were talked about earlier. And these can further cause problems for other organs and tissues like the liver. You can go to the next slide.
Mm-hmm.
So insulin resistance is associated with more pro-inflammatory than anti-inflammatory macrophages, especially in obesity-induced adipose tissue. This is independent of BMI. To go into the mechanism a bit, mTOR-C2 is involved in cell growth and glucose uptake in adipose tissue. But when that uptake is not stimulated by insulin, i.e. in insulin resistance, more pro-inflammatory macrophages are recruited to the visceral white adipose tissue in response to obesity. So there are a lot of downstream effects of these free fatty acids and inflammatory factors. According to the portal hypothesis, which is the fact that, or the hypothesis that the liver is uptaking all of these things that are produced, basically. These inflammatory factors and free fatty acids coming from adipose tissue can damage it substantially. And when the liver is thereafter affected, hepatic fat homeostasis and energy balance are dysregulated, which causes the accumulation of toxic intermediates like ceramides that were mentioned earlier. These lipid intermediates stated before cause issues in general for the skeletal muscle, as Kaled was mentioning. If your muscle is functioning properly, it would greatly counter-effect all the cytokines produced in your adipose tissue. It itself produces tons of myokines that are anti-inflammatory in nature. But an interest...
Sorry about that.
No worries. But there's also an interesting alternate theory, which is that it's actually the growth of adipose cells, or adipocytes themselves, that cause dysregulation. When they grow in a weird way, basically, their morphology does not allow the intake of glucose. And that has to happen before the inflammation. So it's the adipocyte hypertrophy that would be the determinant of adipose tissue insulin resistance, in that insulin can't alter the cell in any way. It's resistant to the glucose uptake, which would have to happen before inflammation. Yep.
No.
Yeah, I can take the liver and maybe connect this to the slide which I spoke about before. This is basically a zoom in of what could happen in the liver, specifically in the case of ethanol, of alcohol. But we should remember, like, the body makes sense. The liver is the one who deals with toxins. Too much glucose is a toxin. Too much fructose is a toxin, and ethanol is a toxin. In the diagram, we can see ethanol coming in up at the left, and you can see the number of metabolic steps that it has to go through just to be dealt with, basically detoxified. So down in the acetate area and the citrate area, we can see that it's it's an oxidation point, so that's already physiologically does some reactive oxygen, like damage, basically oxidative damage. But further to the right, where we can see the blood vessel, and we can see a signal of inflammation that happens, what Jennifer talked about, the hepatic IR happening, because the liver basically shuts down. It says, I'm not supposed to accept insulin, the storage message, when I'm having to deal with toxin. So it further increases the insulin resistance of the liver. And as we can see, it also creates more lipid droplets coming out, regardless of the carbs or food intake. So we have, again, this creation of the arrow pointing out, the free fatty acids coming out, going to the muscle, the adipose tissue, and creating more of this vicious cycle with the free fatty acids going around. So yeah, that's
So
alcohol.
Just another job for the liver to deal with when it's already inundated.
Yeah.
So speaking about other jobs for the liver, we were curious to know, is there a relationship between uric acid and insulin resistance? And the reason is because we do think that the high intakes of certain foods, like, for example, fructose, alcohol, can elevate levels of uric acid. And uric acid can act as a pro-oxidant, and it can trigger the production of reactive oxygen species and inflammatory cytokines, so contributes to the inflammatory process. And there is research saying that it could perhaps be contributing to insulin resistance in this way. However, the mechanism is not clear. We do know that it plays a role in other metabolic diseases like hypertension, but specifically for IR, we're not 100% sure. However, we also know that uric acid in the cells can increase the liver cell sensitivity to triglycerides, and so in that way can also help with the, well, not help, but stimulate the accumulation of triglycerides in the liver, again contributing to this overall cardiometabolic disease picture that we have. So although we don't know the mechanism, how it works directly, we know that it can contribute to the overall picture of insulin resistance.
What happens between, well, to make it short, is that insulin resistance is a state in which our insulin is still coping with the high amounts of glucose, whether from the diet or from transformation in the body, but it's still coping with it and able to store it. And this happens like in the adipose tissue and other tissues, that there is still room maybe for storage, that the pancreas is still growing and able to produce more and more insulin to keep up with that. But the more the body becomes resistant and the storage places become full, the less the pancreas is able to keep up. We actually start seeing damage to the pancreas because at the same time it has to keep up the production of insulin, increasing inside and differentiation. But it takes damage from the excessive glucose and also all this just metabolism that happens there, and even fatty acids that go there. So when that damage starts and the insulin is insufficient to cover the necessity for taking glucose off the blood, we start seeing hyperglycemia, or actually glucotoxicity happen, and high fasting glucose level and so on, which takes us slowly to prediabetes and diabetes. So yeah, building on insulin resistance, we step into the hyperglycemia and the progression of the disease. Yeah, that's basically the term that we've been using. Maybe hyperinsulinemia, so high insulin levels. This is this answers, or this question opens the doors to a little debate. Does the insulin resistance happen before, or is it an issue of high insulin before that leads to insulin resistance in the tissues? So this is a still debatable topic. If you go to the next slide, we can see the two models being compared. So the traditional model says, no, the issue starts with insulin resistance. So maybe in the way we describe the tissues being overloaded with substrate, saying that's it, we don't take insulin anymore, leading into hyperinsulinemia, etc., etc. While in the new model, they say, no, actually the body starts with high levels of insulin that lead into insulin resistance and the rest of the progression that we spoke about. So it's just two different models to take it. No conclusion here.
All right, so we've spoken a lot about insulin in general as a hormone, and it's good to just run over some of the other key hormones that can also play a role. And a lot of this role is related to satiety and how we feel about hunger and our intake of food. And the reason this is important is because we believe that insulin resistance plays a role in obesity, for example, and with satiety. So we know that insulin will increase glycogen synthesis, glyconeogenesis, and then glucagon, on the other hand, does the opposite of that. It's going to reduce glycogen synthesis and increase glyconeogenesis. So those are some of the key hormones. But if we look at other ones, especially leptin, leptin plays a role in appetite. It reduces appetite in the body, and so it causes satiety and stops people from eating. However, there's evidence that leptin is raised in people with larger body masses. This is because it's produced by your fat cells or your adipocytes. And so the more adipocytes or fat cells you have in the body, the more leptin you have, which is meant to reduce your satiety. However, after a point, too much of it in the body creates this sort of syndrome of leptin resistance, and so the opposite takes place, where you then have more hunger, and so it really kind of plays this interesting little dance with insulin in the body and how much food we're taking and having. So that's just a key hormone that we need to think about how it normally functions, and then when there's too much of it, and when we're in this metabolic state, how it then starts to not function as well. Yeah, that's it really. The rest of the hormones all play a role in diet and digestion, and those we're going to be hopefully covered in the future as we kind of discuss the gut more and more.
Cool. Mm-hmm.
Also me. So then it just leads us on to diet and insulin resistance. So this was really key for us to investigate because of our ancestralized model and our look into dietary behaviors. When researching this, we just kind of looked like a broad view of how diets play a role. And so we had a number of different questions to investigate. One of the first was to know, do macronutrient quantities matter when we want to reverse insulin resistance, which is our ultimate goal? And so the research shows like overwhelming evidence that there's more benefit to being on low carb diets when we want to reverse insulin resistance. Other diets can also create weight loss and prevent or reverse insulin resistance, for example, a low fat diet. However, the low carb diet is much more superior in kind of reversing, not only reducing weight, but also reversing some of these processes of insulin resistance. And those sort of diets, for example, like the keto diet, could really play a role in doing that and sustaining that state of reduced insulin resistance long term. And the other key questions were looking at, do certain non-nutrients or metabolically active food parts also play a role in insulin resistance? Sorry, Tyler, I think there's a typo there. It's IR rather than IT. But the answer is yes, they can actually impact satiety. And some research shows that if you are lacking in certain nutrients, then you have this habit of overeating to try to compensate and to try to reach those sort of nutrient goals, not just your macronutrients, but also your micronutrients as well. And then this kind of leads us on to what we call the protein leverage theory. And this is a hypothesis that states that, like, in our human body, we're driven by this need to consume protein until we meet our daily needs. And there's a strong kind of body regulation to do that, not just in humans, but in other mammals as well. And so this overconsumption of low protein food leads to overeating, obesity, and then eventually the kind of emergence of insulin resistance. And part of the issue why we have this now is because a lot of our kind of diets that we have these are high in fat, high in carbs, but very low in protein. And so we overeat to try to compensate for that. And so one of the best ways to do that, or to reverse it, is to make sure we're meeting our protein needs every day. And that can really help. And then finally, there was some evidence showing that addition of other things like sweeteners, although they may not directly impact insulin resistance in the way that like kind of carbs could, they may contribute to other problems in the gut, like gut dysbiosis. And so that's something to also be wary about when you're trying to look for alternative food sources. So what diet causes remission? We've sort of touched upon that as well. Weight loss will help with reducing insulin sensitivity in insulin resistance in the body, improving sensitivity. But really, if you want to reverse or put your body in a state of insulin resistance remission, then looking at low carb diets, especially very low carb diets with high fat, such as the ketogenic diet, these can play a role. Low carb in general reduces this postprandial or post-meal hyperglycemia and hyperinsulinemia, and over time, as that kind of becomes the new normal state, then you start to improve insulin resistance and you stimulate this remission. Of course, dietary adherence rates are influenced by individual preferences, cultural and socioeconomic factors, but really going towards a kind of lower carb diet will kind of help with this metabolic picture overall, and that's the best option.
Awesome. One thing I would point out on this slide is number one, we listed low carb diet and low fat diet. I think that that's a really interesting distinction to make, because so much of insulin resistance is, like we were talking about earlier, a substrate problem. Is that you're inundated with too many different fuel types, some need to be prioritized more than others, and as a result, others are just automatically stored and can accrue quite rapidly. So one of the key features of a diet that avoids this is to prioritize one substrate at the expense of another. So a very low carbohydrate diet is not only effective because fat is high, but because carbs are low, and therefore you're leaned heavily towards beta oxidation rather than normal cellular respiration. A low fat diet, which I wouldn't say is our personal preference, but would achieve the same thing, in that you are going to lean almost exclusively in cellular respiration. You're going to have very few fats that you're going to have to beta oxidize, and that you wouldn't get the same kind of influx of too many substrates in the same way. Granted, that comes with its own slew of problems with the glycemic variability of different foods and insulin response, specifically for insulin resistance. Having a diet that's high in carbs wouldn't be ideal there, but at least prioritizing one over the other speaks to the overall substrate problem that we see a lot with this metabolic conditions.
Yeah, and maybe it's a good place to go back to the hormones controlling this these events is, and at the center of that is insulin. Is the thing is when, okay, let's get back to high school biology. There is catabolism and anabolism. Anabolism is what makes us big and fat and
and muscular.
Sorry.
Yeah,
and muscular possibly,
Yeah.
if the routine is the right one. While catabolism, I like to remember a kata, cutting or breaking down. It's what breaks down tissue and lets us consume what we have. Insulin pretty much is kind of the boss here. If there is too much of insulin, it's going to say, okay, now we store, we calm down. It's a bit like the parasympathetic sympathetic dichotomy in the body. If there is insulin, it's storage mode. And that obviously, as we described before, is not good if we are already storing too much. On the other side, there is glucagon, and the right column of the slide that Wafa described before, with all those hormones and molecules that tell the body to break down stuff. So let's come back to this. More insulin, more storage. Less insulin, less storage, which also translate to more breakdown of the fat storages and lipolysis, breakdown of these lipid storages, and so on. So we might prefer a diet that takes us to that stage of low insulin, more breakdown. And ketones are an interesting case because when there is few insulin, so the message to break down the lipids and create ketones is not disturbed anymore. So when we lower insulin thanks to a certain diet, we get more of these ketones, like more efficient fuel, basically, more breakdown of the storage place. And also ketones are absorbed seemingly so far as we found without the need of insulin. So all further reinforcing that the more we go into low insulin, if it's not a pathologic state of the body, then the better the diet is and the better the control of these fatty acids is. Yeah.
An example I like to think of is, I'm sure we've all seen videos of people in Asia trying to get on public transportation trains, and they have the designated pushers, people who are trying to cram as many people into the train as they possibly can. Insulin's the pusher. And if the end goal is to get people off the train, we need to reduce the amount of pushers we have. Otherwise, it's just antithetical.
We need push-out personnel.
Yeah, exactly. I think the pressure of the hundreds of people crammed in that train is sufficient to get them out as well. Okay, so clearly we have a preference towards a ketogenic diet. So what exactly does ketosis and or ketone bodies do in the body to actually help reduce insulin resistance? So a ketogenic diet does a lot of things. And you'll see in this diagram that we have dietary protein is often increased. Ketone bodies are produced, reduced carbohydrates, fibroblast growth factor 21 goes up, and we see GLUT transporters also getting upregulated, or at least increasing sensitivity because they're not being inundated as much. So what does this actually translate to? So with regards to dietary protein, like we mentioned before in the protein leverage theory, is that when you prioritize protein as a macronutrient, and granted there are many different kinds of ketogenic diet ranging all the way from moderate to high protein consumption, but prioritizing that as a macronutrient of concern, we can often, if we meet that goal, overall satiety cues can be reduced. So the overnutrition, first step of this whole domino effect, can be avoided or at least reduced. Protein is also the most satisfying or satiety inducing of the macronutrients. So the more protein you eat, generally the better calibrated your hunger signals are going to be. And it may be easier to be compliant with a high protein diet than one that's lower in protein. With regards to ketone bodies specifically, you can see that they have a lot of anti-inflammatory effects. So actual inhibition of a lot of inflammatory cytokines and transporters. They also produce fewer reactive species in their production. So compared to normal electron transport chain mitochondrial functions like we were talking about before, the action of producing ketones produces fewer reactive species. So in general, as an energy substrate goes, they tend to run cleaner is a common narrative that we hear with ketones versus glucose. What this often translates to is there are fewer metabolic consequences by using that as a, you could say, a full-time energy substrate, or at least giving your body a break from one versus the other. So things like non-alcoholic fatty liver disease, which was a consequence of there just being too many triglycerides, too many free fatty acids that needed to be stored elsewhere. Being a ketogenic diet gives you the opportunity to lower your glucose intake. So the actual glucose that your body does need, it can be pulled more effectively. Triglycerides can be liberated from tissues because they're no longer getting that insulin pressure to be stored. And overall, we can start to see ectopic lipid accumulation start to be reduced. And one of the most obvious places of that is the liver. The other is, to Kaled's point, we start being in a more catabolic state when we're in ketosis. So things like autophagy are increased quite a bit, cellular self-cleaning. And as a result, a predictable result of being in a catabolic state, we see body tissue start to, or body fat accumulation start to be reduced as well. So weight gain is a natural consequence of the fact that we essentially are using the substrates that we already have in the body rather than relying on new ones. And while this isn't talking about type 2 diabetes specifically, it's intrinsically tied to insulin resistance because a ketogenic diet is going to have less of a glycemic effect, thereby requiring less insulin to be present for the metabolism of that substrate. Your cells will be exposed to less of it and can thereby regain some degree of sensitivity, which is sort of the entire point, is that the insulin that you do have and necessarily have will be more effective at lower doses. Other conditions like PCOS, we can talk about aromatase, the transfer of testosterone to estrogens, but other conditions that rely on insulin's actions in different cell types will also improve with improved sensitivity. And fasting. So ketogenic diet has a lot of major benefits. One of the major ones is that it has often been referred to as a fasting mimicking diet, not to be confused with the actual fasting mimicking diet. But so the actual hormonal profile of a ketogenic diet is very similar to when you're in a fasted state, which speaks very much to the whole catabolic argument that Kaled presented earlier. So when a person is fasting, their insulin levels are obviously at absolute base levels. If somebody has chronic insulin resistance or hyperinsulinemia, they may still be above basal levels for a normal person, but for the person in question anyway, they are reduced to the maximum extent because there's no glycemic impetus for it to be raised. This not only allows us to switch into a catabolic state in which we liberate our own fatty acids from different tissues, it allows us to regain insulin sensitivity, and other things like leptin and the other hormones that were discussed can also begin to regain sensitivity in those tissues just because they're not being dominated by a overzealous insulin response. Does fasting have as much of a beneficial effect in the presence, like when given alongside a ketogenic diet versus somebody who is on, say, a standard American diet? I think that it's reasonable to say that probably not as much. So if somebody is following a super low glycemic diet, a lot of the benefits of fasting, or the chief benefit of fasting at that stage, is just general calorie restriction. Whereas if we're talking about somebody on a standard American diet, fasting is useful for calorie restriction as well as the hormonal benefits that you would be providing your body during that 16-hour or 24-hour fasting period. So even though you are still going to be incurring glycemic burden later when you do eat a standard American diet, you at least have given half of your day, at least, if not longer, to give your body a break, regain some of its sensitivity, let hormone levels regulate between, and not be subjective to the chronic spikes of constantly snacking or just mindless eating. The keto flu. It's impossible to talk about the ketogenic diet and not have people be at least somewhat aware of the fact that the keto flu is a thing and who it could generally affect. So right off the bat, the keto flu doesn't affect everybody. And the exact mechanism of what the keto flu is not completely elucidated, but we do have some theories. So the keto flu seems to impact roughly 50% of people that adopt a ketogenic diet. There are a lot of theories on why that happens. Certainly, it's been implicated that the degree of insulin resistance the person had prior could predispose them towards getting a ketogenic flu. Other things point to electrolyte imbalances, and that increasing sodium in electrolyte intake can often ameliorate keto flu symptoms. But the keto flu is essentially the manifestation of your body throwing a tantrum, in that it isn't using the energy substrate that it's become accustomed to. So if you were in a dominated metabolic state of cellular respiration, you've eaten glucose, throughout your entire day for the past 20 years, and you didn't know about any of this, then your body probably has been very heavily reliant on regular cellular respiration, electron transport chain metabolism, and maybe has had very few opportunities to actually explore beta oxidation, which is just as useful, but has been largely suppressed because of insulin's presence. When you do switch over to a ketogenic diet, you are forcing your body, or even fasting in some cases, the keto flu can be present with some longer duration fasts. You're forcing your body to use beta oxidation. And the cellular machinery that was involved in that process is largely or we could at least hypothesize, is in disrepair. So the actual investment in energy at that stage to repair the cellular machinery, to get accustomed to producing ketones, to other tissues in your body using those ketones, even though they were absolutely capable of doing it physiologically, just practically, it's a pretty novel substrate for the body to be using. This slow adaptation to a new energy substrate and really moving your metabolism in a different direction is largely what's considered to be the cause of the keto flu. And we see symptoms begin to ameliorate as we see ketone levels rise, implying that this really is a substrate production issue, and that the better you get at being in ketosis, the less your body needs to throw a fit when it's asked to be in there again.
So the next question we kind of asked on this journey was, who should not go on a keto diet, if any? And there are very few kind of people who shouldn't be on a keto diet, or it doesn't work for them. But there are specific disease groups or kind of histories where it's good to think about what that condition is before you start on a ketogenic diet. One of the first would be eating disorders. Because of the kind of history of disordered eating behavior, anyone with an eating disorder will need to be well monitored while starting on these kind of ketogenic diets. And it's the same for any sort of restrictive diet, not just the keto. But if you've got a pattern of disordered eating, then it's important to have it monitored by a health practitioner to prevent episodes like binge eating, for example, from redeveloping. That being said, it doesn't mean that the keto diet will not work in these cases. It actually will likely reduce carb cravings and can be quite beneficial. It's just about monitoring. The other important groups to think of are individuals with end-stage kidney disease. Again, there are studies that show that people with kidney disease can be put on ketogenic diet. However, we need to remember that when we first start a ketogenic diet, you do get this initial sort of diuresis, I think that's how I pronounce it. But anyway, you're releasing a lot of fluid from your body, and if your kidneys cannot handle that, then you need to be careful with it. And especially if you are on dialysis, then this is where monitoring from a health practitioner is important. Other cases are acute intermittent porphyria. This is an autosomal dominant inherited metabolic disease. With this patient group in general, you should avoid any kind of prolonged fasting, and diets should be consistently high in carbohydrates. And so in that case, the ketogenic diet, which kind of mimics a fasting state and also has very low carbs, may not be the best for this particular patient group, because it can or may induce an acute attack of the condition. So definitely something to be wary of. Primary carnitine deficiency is a genetic disease where there's a mutation in one of the genes that codes for a protein, and this transports carnitine into the cells, and this carnitine will then help with the breakdown of fatty acids. If you are deficient in this protein, or at least the transport protein to get it into the cell, then being on a kind of high fat diet may lead to buildup of fats in the different cells in the body. And so one way to counteract that, there have been success studies where being treated with a supplementation of carnitine can actually help in these deficiency cases. It is quite rare to have, but it's also something to think about. And then hemochromatosis as well is really important. You tend to be on higher amounts of meat in general on a ketogenic diet. You are on high fat as well, but you are getting high protein in meat, and that could be a source of dietary iron. And especially for people with hemochromatosis, that excess iron can worsen their iron overload, and it's something to also think about. So yeah, so there are some specific cases where you need to just really think and have monitoring by professionals before you start. But for the majority of people, it's safe to start and go do it. Next one.
Mm-hmm.
The other key ones to think about are diabetes and the ketogenic diet. So type 1 diabetes is interesting because there is evidence to show that patients who've been started on a ketogenic diet, even though it's not a metabolic disease and it's related to antibodies, actually starting them on a ketogenic diet can help with symptoms of hyperglycemia and can help the disease state overall. Really, the key thing to think about in these cases is that often, well, any type 1 diabetic is on insulin anyway, and reducing carbohydrates while still on insulin can result in episodes of hypoglycemia, and there's an increased risk of that if that kind of dose of exogenous insulin isn't altered beforehand. So although this patient group can be started on a ketogenic diet, it's important to adjust that insulin dose because your need for insulin is going to reduce as you reduce your carbohydrate intake, and that's important to do. It's also really important to closely monitor for signs of diabetic ketoacidosis, and just be wary that that could be a possibility in these patient groups in general. So just to be mindful of that. With type 2 diabetics, even though they may not be on insulin, especially in earlier stages of the disease, being on anti-diabetic medication kind of does the same thing. You're taking the medication as you're kind of having this high carb intake. While you start reducing that high carb intake, the effect of that anti-diabetic medication may be more powerful than what you need. And again, it can, especially with certain medications like sulfonylureas, they can also push a person towards hypoglycemia. If the carb is too low and the anti-diabetic medication is too high. So modification of that drug dose before starting the diet, and being aware that you may need to start reducing your drug dose as you progress in the diet is important for diabetics in general. That being said, they can still be started on these keto diets, and there have been studies to show that this is the case. It's just about monitoring the risks.
All right, something hopefully less complex to achieve is getting good exercise, and that's really good for everyone. And it's a big determinant of insulin sensitivity, as written there. If we go back to that diagram with maybe the liver being the packaging department and the factory, while the adipose tissue is the warehouse, the storage place. If you would say that that's the energy company, I would say the biggest client, the biggest user of energy is the muscle, responsible for 80% of glucose uptake. Obviously, the muscle is the biggest client for energy, maybe the brain after that, but we can start thinking this way, and that helps us to see like how much exercise and movement and using that muscle, the stored substrate, is important. So back to the slide, for example, what it can do is that basically the insulin-induced glucose uptake improves thanks to exercise, some of it directed to glycogen synthesis, some of it being the basal intake just for upkeep. That which is sent to storage is mainly mediated through the GLUT4 transporters. Recently, I found out that there are many of these GLUT things. GLUT1 is non-insulin dependent, which is good to activate, and thanks to exercise, it's more expressed. So our basal use, even as they say after exercise, you still use some of the calories. Yes, it's true. It's just the basal use rises, as well as the storage kind of use that is mediated through GLUT4, that is moved to the plasma membrane and makes insulin more efficient and functional in the muscle cell. Basically, it sensitizes the muscle to insulin again. And if we leave the glucose and the carb story aside and glycogen story, we can look at the fatty acids again. Remember also that fatty acids are a big component of this pathophysiology. So yeah, when we exercise, we get more use, more oxidation of the lipids that are stored, and more mitochondria, more efficient mitochondria, which helps us oxidize those lipids that might have accumulated in the muscle cells and just be more efficient energy machines. It's definitely good.
Yeah, one other thing that isn't mentioned in this slide is also you did a great job of illustrating the importance of muscle in general, lean body mass, and to that point, more is, maybe not at the expense of taking steroids, but more is better in that you have more demand for glucose. Your ability to store more glycogen improves. Just generally, your glucose disposal mechanisms increase substantially. So, and there's no better way of increasing your lean body mass and muscle mass than exercise. So, short of the actual acute effects of your body undergoing physical activity, the long-term effects and your actual capacity can expand as well.
Yeah, almost forgot also that because it's a dear topic, the endothelial and the vascular system is also wrapped by muscle. And that little muscle, as we said, is the most sensitive to high glucose and glucotoxicity and insulin resistance. So thanks to exercise, we get better vascularization and more vascularization, which again helps us also deal with those early symptoms. And yeah.
Okay, so there are multiple other potential contributors of insulin resistance besides diet and exercise. Aside from genetics, epigenetics, which obviously play a role, other pathologies like liver problems, non-alcoholic fatty liver disease, which has some of the same underlying mechanisms, disease mechanisms, oxidative stress involved with the liver, and also thyroid diseases are involved in the same metabolic pathways as insulin resistance, so they can co-occur. Circadian misalignment, which is another interesting idea, which if you are misaligned and you're having sleep issues, this can upregulate cortisol and can change your appetite, maybe causing you to eat more or less, or just creating in generally an imbalance. Gut dysbiosis and incomplete digestion, and possibly some specific intermediates have been shown to co-occur in people that have insulin resistance. Oh, and sorry, deficiencies. Specifically magnesium deficiency, because it's implicated in some of the mechanisms of insulin transport, is often seen in insulin resistance.
Cool.
Continuation of other contributors. So we know that a lot of toxins are ubiquitous and basically unavoidable in our environment. There are quite a few that seem to be involved or have epigenetic effects with obesity, like obesogens in general. And all of these excess toxins can put strain on the liver in general, which we know is a huge factor in insulin resistance. So like common endocrine disruptors that are in plastics, BPAs, have epigenetic effects and can cause issues with pancreatic beta cell insulin content. Nitrosamine compounds, which are found in cigarette smoke, have been implicated. POPs, mostly found, there's mostly animal studies concerning persistent organic pollutants, can alter the regulation of lipid homeostasis. Other toxins, like the polyfluoroalkyl chemicals, are implicated in cholesterol dynamics, and also cadmium, so heavy metals, being exposed to heavy metals. Another thing that can accumulate in your tissues, cause problems with the liver, have been shown to co-occur as well. Another major thing is all of these are found in the environment. Like I said, they're basically unavoidable. But studies that investigate the compounded effects of them, because they commonly co-occur in our body, are definitely not as easy to find, and maybe just haven't been conducted yet, which alludes to this fourth bullet point on here, where they looked at 9 common chemicals and the joint effects of them in general in your body, in circulation.
This list is great. There are a couple interesting things to point out too. So as far as where the rubber hits the road, where do people actually confront most of these? It's like you said, plastics, a lot are used in agriculture, so non-organic foods, persistent organic pollutants, one of the major sources is eating higher up in the trophic food web, essentially. So that's why it's generally more hazardous to eat things like swordfish or tuna, things along those lines, because they've had a chance to bioaccumulate these persistent organic compounds. And another thing is when it comes to our body's able to biotransform a lot of these, though very difficultly, and difficulty is not a word. It's very difficult to do so, but it comes at the expense of a lot of micronutrients that are required for that to begin with. So understanding that we are all exposed to all of these and that our best chance to be able to biotransform them out of the body often means that we are more nutritionally deficient than we would otherwise believe in the absence of these chemicals being here. So if we're supporting phase 1, phase 2 detoxification pathways, you have a higher requirement for amino acids. You have a higher requirement for B vitamins. Ultimately, a lot of these, when we accept the fact that they are probably in our diet in some form or another, the requirement for nutrient dense rather than calorie dense foods is also increased. So just a quick addition there.
And also, if you're doing detox, or if you're trying to lose a lot of fat, or a lot of these other things, I didn't mention dioxin in general, but if you're losing fat rapidly, you then have them in circulation more readily, and that can cause other problems to your liver. So it's something that definitely needs to be considered in weight loss.
Yeah, rapid weight loss needs to be accompanied with a super nutrient dense or even supplemental regimen to compensate for the amount of toxins that are going to be liberated from your fat cells. Right. Okay.
Oh. Sorry, can you go back?
Yeah.
So this is a compounded question. All of these things interrelate. So what role does infant weight, childhood obesity, maternal obesity, and gestational diabetes play in the future likelihood of developing insulin resistance? So first, talking about maternal obesity and gestational diabetes, pregnancy in general induces overall metabolic stress and a slight insulin resistant state. It also upregulates leptin because you want to make sure that you eat enough to also feed the baby that's growing. So on the left-hand side, obesity in general is more strongly correlated with childhood adiposity than gestational diabetes. The relationship is a little more murky because they both have a lot of underlying pathogenesis and those sorts of things. They're related, but it's interesting that one correlates a little more strongly in the future development of childhood obesity. So diabetes in general during pregnancy, or specifically when it develops during pregnancy, like not before, specifically during, because of like the metabolic stress that I mentioned. It's a strong predictor of the development of metabolic syndrome in the children and the offspring. And approximately 20% of gestational diabetes offspring develop diabetes themselves or prediabetes by the age of 22. So in terms of those implications for the baby when it's born itself and in adolescence and childhood, being a premature baby or a larger baby can throw off sort of your metabolic regulation in general, maybe because of those factors during pregnancy. And there are a couple hypotheses for this, or well-known sort of groups of mechanisms in literature. So there's the thrifty gene hypothesis, and then there's the catch-up growth hypothesis. Thrifty genes alludes to the fact that there were evolutionary mechanisms in place for us to adapt to famine period. So if you're a really premature or small for gestational age baby, you might sort of be more predisposed to having genes that can cause obesity later in life. It's a little bit different than the catch-up growth hypothesis, which might be also caused by some similar genetic factors, but if you were small for gestational age, you might end up gaining a lot more weight in adolescence. And of course, there's a lot of epigenetic and environmental factors that go into this. But in general, given that your infant weight can somewhat predict or cause obesity in childhood, obesity in childhood in general has future implications. So no matter when in childhood you were on the larger end or of BMI or were obese, it has future consequences. So like 60% of children in the highest BMI quartile transition to highest BMI quartile as young adults. So obesity, no matter when it happens in your childhood, can follow you for the rest of your life. And also no matter how long you were obese for in your childhood, it's that metabolic state in general, probably because you're a growing individual and it might alter your metabolism and your bodily, I don't know, physiology in some way. So childhood and adolescent obesity might evolve into metabolic syndrome in type 2 diabetes in youth and in adulthood. And what this boils down to, this picture, is basically a vicious cycle where if one of your parents was or is obese, or if when you were in utero, you were exposed to those epigenetic factors or hypoglycemia, it increases your likelihood of being obese as a child, which then increases your likelihood of being obese as an adult. And then the cycle continues because if you're pregnant and you're a female or a male also contributes, but then the just cycle keeps going on. So it's almost like it creates this exponential growth of obesity and diabetes, at least by this mechanism. That's it.
Okay. So yeah, at least on to Jennifer's last point before we totally close this out. In my mind, it's really tough to parse out between what's environmental and what is not when it comes to familial incidence of developing obesity and diabetes and insulin resistance. How much of that is the eating behaviors, the food environment that you grew up in and that you perpetuate into the future versus actual genetic, risk factors or your epigenetic expression to those environments that persists even after you've left that environment. It's really hard to parse out. But I will say the thrifty gene hypothesis, maybe it's just because we're ancestralized, but finding the evolutionary impetus for why metabolic diseases are more likely to accrue, I think is just perfect. I think that if you're born in a food scarce environment, your genes intentionally skew you towards, substrate accrual and, thrifty energy balance. And it's only in the modern context that could be abused wildly out of control, which is, it just seems super ancestralized.
Also, the founder's effect and this principle of if in our evolutionary past we were going to a new environment, those who were able to catch up in terms of their weight gain and their strength at post-famine and persist after a famine because they had a metabolic advantage to gain weight would be more selected for in populations. So that's why maybe in certain populations you see more rapid and easy weight gain.
And if those populations historically were exposed to more famine.
Yeah.
That's really interesting. Okay, well, thank you, everybody. This was essentially the main takeaway points for insulin resistance. Obviously, it's infinitely more complex than the actual detail that we went into, but these are the major, I think, the most practical points. So there is a whole mountain of other correlative influences or things that are just harder for actual users or they're harder to test for, what we would implement in an actual treatment protocol. But more or less everything that we discussed has some real world application that a person could leverage to a certain extent to improve their chances of reducing insulin resistance. So far be it from being completely comprehensive, but at least largely actionable. But yeah, I mean, any other comments or anything from anyone in the group? All right. Well, thank you all for presenting and for all your hard work in putting all this together. We'll end it here.